and welcome back to another video. Now today we have another viewer request. So let's see who it's from this time. Okay. Dear Edmund, please can you help me with this problem? Right, what have we got here then? I want to find x in terms of a and c only. Thanks, you and Dennis. And I'll just show you what's on this piece of paper here. You can. Okay. Well, that's no problem. I'll see what I can do. Okay. So we just to show you, make it absolutely clear, what we're looking at is a circle, and there's a chord line, and this chord line is of length c, and we have this arc length, which is length a, and we have some distance x, which is in the middle, bisects this chord line, and we want to find this value x in terms of a and c. So the approach I'm going to use is, well, draw a diagram. I just want to do that, but that doesn't really help with the maths. Well, it does, because now we're happier. Anyway, so we have this chord line, and it invites us to think about an angle. This angle theta here, and of course we have the radius of the circle, which are these two lengths here, if this point here is the centre of the circle. We've also got this length c, but I'm going to split this into, because it's quite natural to think of this kind of thing as a right angled triangle. I'm going to split this into c over 2 and c over 2, knowing that, of course, if you add them together, you get c. And finally, of course, this is the bad boy. This is the length x that we actually want to solve for. And finally, we have this other length a, which is some other parameter that we want to express this solution in, express x as rather. Okay, so what we have is we have 5 variables. We have r, theta, and we have a, c, and we have x. Now, we want to express x in terms of a and c only, and we don't want these to be in our equations. However, in order to get the right relationships, we will need to use these. So we will need to find some equations to eliminate these. And if we have 5 variables, then we need to have 3 equations to essentially eliminate 2 of the variables and be left with just these 3 variables. So we're going to think of 3 equations that we can use to relate these 5 variables, and then hopefully solve it and find x in terms of a and c. So the first relationship I'm going to use is the arc length formula. So we can use that essentially this a is an arc length, we have an angle theta, and we have a radius r. Now, just by the definition of the radian, we know that the arc length a is equal to r times theta, and actually you can derive that directly from polar coordinates, where theta is measured in radians. Because of course all equations are nicer when they are expressed in radians. The second formula, so I'm also going to call this equation 1. And the second equation, we're going to use Pythagoras. So if we use Pythagoras, now if we take this triangle and put it outside, this is a right angled triangle, and one of the lengths is c over 2. One of the lengths is r. And one of the lengths, well, the other length is this length here. I'm going to use a different colour now. I've got these new pens. I'm going to, let's crack out the brown pen. So we have this other length here. Brown pen isn't very good. And what is this length? Well, we know that this length is the radius, r. So it's just r subtract x. So we know that this is just r minus x. Okay. So, now we can use Pythagoras on this. And we know that r squared is equal to r minus x squared plus c squared minus 2. So we therefore know that r minus x squared is equal to that squared minus that squared. So we have r squared minus c squared over 4. And indeed, we can just take the square root of both sides, and we get this, over half. And I'm going to call this equation 2. Okay, finally, we can use the cosine rule. Because we have this triangle here, this big centre triangle, where this long length is c, and the two short lengths are r, respectively. And we have this angle theta in the middle. So using the cosine rule, we can say that, we have c squared is equal to r squared plus r squared plus 2 times that, so it'd be 2r times another r, so that gives you r squared, times by cos of theta. And we can simplify this, of course. This gives you c squared is equal to, now what I'm going to do is, this is going to be 2r squared, of course, and then you can factor out the 2r squared, so you get 2r squared times by 1 plus cos theta. And I'm going to call this equation 3. Okay, so I'm just going to write all my equations up there, and then we can use them to solve the problem. So we have a is equal to r times theta. I'm going to call that equation 1. We have r minus x is equal to r squared minus c squared over 4, and I'm going to call that equation 2. And that's to the power of a half. And we have the cosine rule, we have equation 3, which is c squared is equal to 2r squared times by 1 plus cos theta. Okay, and I'm going to rub all this off. Okay, so we can start off by looking at the easiest equation, right? So we can start off with equation 1, and equation 1 implies that if we divide both sides by theta, then we get a over theta is equal to r. Now we can, of course, we want to get rid of r. R is one of the variables we don't care about because we only want it in terms of a and c and x. So we're going to eliminate r in equation 2, so we're going to sub into 2. So we get that a over theta minus x is equal to r squared. Now r is a over theta, so we get a over theta all squared minus c squared over 4 to the power of a half. Okay, and of course that simplifies very nicely because this a, it doesn't simplify nicely, but, well, actually, it does simplify. It does simplify nicely because you can take the square of both sides. Here comes the brown again. Not sure if you can read that very easily, but here we go, that's a squared. And then, of course, when you square this side, the square root cancels with the squared, so you just end up with the thing on its own. And if you expand this squared, you get a squared over theta squared minus 2 times that, so we get a over theta times x plus x squared is equal to just this thing on its own. So we get a squared over theta squared, of course, from that term, minus c squared over 4 from that term. And of course, the a squareds over theta squares cancel nicely. And we can now bring this term to that side. We want to get rid of these nasty minus signs. So we can take this minus c squared over 4 to that side, the 2ax to that side. So we get x squared plus c squared over 4 is equal to 2ax over theta. Now, if you just flip over those equations, we get this to the power of minus 1 is equal to this to the power of minus 1, which is just going to be theta over 2ax. Now, if we simplify and solve for theta, then we get, therefore, that theta is equal to 2a times x divided by x squared plus c squared over 4. All right, and I'm just going to write this equation up there because we're going to be using it again later. So I'm just going to write this. And this is going to be our equation. Let's call it equation 4. Equation 4. Okay. Right, so that's that bit of work done. So where are we going with this? Well, let's just rub this off first. And we're going to now examine the third equation, which is equation 3. Now, if we recall, we know that r is equal to a over theta. Let's substitute into equation 3. So that implies that c squared is equal to 2 times a over theta squared. And we're also going to, actually, let's not do that yet. That's a bit of a dangerous game to do at the moment. Plus 1 plus cos of theta. I'm just going to simplify this. This gives us a squared over theta squared. And then I'm going to move the theta squared up there, so we get c squared theta squared over 2a squared. So I'm just putting all that down there, is equal to 1 plus cos of theta. Okay, now essentially we have essentially solved the problem now, because we've got a relationship for theta, and we know what theta is in terms of x and a and c, and we know this equation only involves c and a. So the solution to the problem essentially is you use x and c and a to work out theta. You then plug theta into this formula and your known values of c and a into this formula, and then you will solve this equation, and then you can work out what x is. Or rather, the other way around, you'd put c into here and a into here, you'd solve this numerically, and then you'd solve this equation for x. Now, we can't, the reason why I say numerically is because actually this is a theta squared, this is a cos theta, and there is no way you can solve this equation using elementary functions. So, but the best thing, what we can do is we can prove that a solution does exist. So what I'm going to do, and what we're going to do now, is that prove, in order for us to get a value x, we need to show that there is actually a solution to this equation. So I'm going to write this equation up here. So we get c squared, and what I'm going to do is I'm going to define k as c squared over 2a squared. So I'm going to say k is identical to c squared over 2a squared. I'm just defining it that way. Therefore, our equation becomes k times theta squared is equal to 1 plus cos of theta. We want to prove that solutions exist to this equation. Now, well, the problem is we don't know what k is. However, we can put a bound on it, because we know that A is this long length here. Well, yeah, here's a simpler diagram. A is this long length here, and C is this shorter length. So we know that C is less than A. So we know that C over A is less than 1. So C squared over A squared will be less than 1. So therefore, C squared over 2A squared will be less than a half. Oh, that's our K. So therefore, we can say confidently that K is less than a half. So what we're now essentially solving, what we've boiled this down to, is proving that solutions to this equation exist where K is less than half. Okay, now, so the way to prove that a solution exists is by showing that if we plot the graph of this side, then and we also plot on the same set of axes the graph of this side, then there should be an intersection. So let's do that. So we have some function f of theta, and some value theta, and I'm first of all going to plot my k over theta squared, and I'm going to use my red pen for that. So k theta squared, well, that's just going to be a quadratic. Actually, no, I'm not going to do that first, and you'll see why in a minute. Apologies for that. So I'm going to use my purple pen and plot my 1 plus cos theta first. Okay, so now, is that 1 plus? No, that's, damn, I made a mistake. I made a mistake earlier. That should be a 1 minus. As I'm sure many of you we're aware. Yeah, that should be a minus. Sorry about that. Okay, so 1 minus cos theta. Well, we know that cos theta looks like this. That's sine theta, not cos theta. Don't know why I said that. We know that cos theta looks like this. So if we do minus cos theta, then it will look like this. And then 1 minus cos theta is just minus cos theta add 1. So we know that the graph of 1 minus cos theta will look something like this. My purple pen, there we go. It'll be like a big thing, and then it'll be down again, and then this will be theta equal to 2 pi, and this will be theta equal to pi. Alright, so what about k theta squared? Well, k theta squared we know is a quadratic, and k theta squared we know will have this shape. But it could do one of two things, right? It could either do this. We know it goes through the origin. I'm just going to make this clear that this is indeed 1 minus cos theta. Or it could do this. If it's a very wide base, it could do that, and then it will go up, and then there'll be a solution there. So, which one of these is it? Well, thankfully we know something about k, so we can hopefully figure this out. Now, if we I'm just going to call this y of theta, because I'm going to say that f of theta, I'm going to say f of theta is identical to k theta squared, and g of theta is equal to 1 minus cos theta. So essentially this is a plot of f of theta and g of theta respectively. Now, we know if k theta squared has a gradient that is smaller than 1 minus cos theta, then we know it will do this. And if the gradient is greater, then we know it will do this. So let's examine the gradients of these two functions. So f prime of theta is equal to 2 times k times theta. Well, we know that 2k is less than 1, so we know that this will always be less than theta for all values of theta. But it will still be a straight line function. G of theta, on the other hand, g prime of theta will be equal to, well, the 1 goes away, and then the minus cos becomes a sine. And if you think about the graphs of sine theta and theta, I'll just call this y again. If you look at sine theta, we know that sine theta does, let me get this right, it does that. And we know that the graph of theta will do, well, if we know that when theta is small, sine theta is about the same as theta, so we know that the gradients are the same at the origin. But we know that when the gradient of this line is greater than 1, then this straight line will never meet sine x again. However, if we have y is equal to some gradient k times theta, where k, let's call it m theta, where m is less than 1, then we know that the gradient at theta is 0 is definitely less than 1. So we know that essentially the graph will do something like that, because the gradient of the function is less than sine theta when theta is 0. Now that gives us confidence, because essentially this is the same thing as this, so therefore we know that that 2k theta will be less than sine theta near the origin of the above. So we know that around here, the gradient of 1 minus cos theta, which is sine theta, will always be greater than the gradient of k theta squared. Now that means that because this gradient, the gradient of the purple line will always, well, certainly near the origin anyway, be greater than the gradient of the k theta squared line, we know that this must be the one that the k theta squared looks like. We know that it must be fall this side because there's a lower gradient near the origin. So we can forget about that, and therefore we can now see that a solution does exist. It's right here. And it will be some positive real valued value of theta. So we can rub all this off. So we've proved that solutions exist to this equation, which is very exciting. That's fantastic, because now we know that pretty much we can put in our value, and actually let's put in our c squared 2a squared again. We don't need you anymore, okay? We can say with confidence that this equation has solutions where theta is greater than 0, as you saw on the graph, and theta is a real number, which is great. So now that we've proved that solutions to this exist, all we need to do now is prove that solutions to this exist, for x, that is. So if we examine equation 4 again, then theta is equal to 2ax over x squared plus c squared over 4. If we multiply both sides by this and bring that up, then we get, and divide by theta, then we get x squared plus c squared over 4 is equal to 2ax over theta. And I'm just going to subtract that 2ax over theta to make it look like a quadratic equation. Let's make sure I get this right and don't make a mistake this time. Yep. Minus that plus c squared over 4 is equal to 0. Okay, so this is a quadratic. Let's solve this quadratic in terms of theta. So we have x is equal to minus b, now b is 2a over theta, plus or minus b squared, that's 4a squared theta squared, b squared minus 4ac. So we have 4 times 1 times c squared over 4, the 4's cancel, so we get minus c squared to the power of a half, and all divided by 2a, which is 2. Okay, so we're almost home and dry, but we have a square root here. And if this stuff inside the square root is negative, then x will be a complex number, and that will really mess things up because x has got to be a real number greater than 0. So we've now got to prove that this thing inside the bracket is positive for this to work. So let's examine 4a squared over theta squared minus c squared and just see whether or not this is greater than 0. It better bloody well be greater than 0. So we can shove in our value of theta, because actually theta we're talking about a length a here, and comparing, a length to a length with an angle isn't all that useful. So we want to see if we can compare a length with just compare lengths. So let's plug in theta. So we know that theta is a over r. So therefore 4a squared over a squared divided by r squared, because I'm basically just squaring that. Oh, the a's cancel, a squared's cancel, that's great. Minus c squared, and we want to check if this expression is greater than or less than 0. We have 1 over r squared and we have 1 over that, so the fraction will come up. So we're examining 4r squared minus c squared, and we want to decide, is this thing greater than or less than 0? Well, 4 times r squared, what does that look like? Well, that's 2r, that's just 2r all squared. So you can safely say that that's a bit of bad 2 there. There we go. That's 2r all squared. And is this thing going to be less than or equal to 0? Well, we're pretty much comparing r and c. So if we look at r and compare it to c, now remember c is the length of this chord, and 2r is this fixed length here. Now you can see that just clearly from this diagram, C will always be less than or equal to 2r. Because, you know, it's clearly always shorter no matter where you go, and it's only equal to 2r. C is only equal to 2r when it overlaps here, and that's the case when theta is equal to pi radians. So we can say therefore that c squared is less than or equal to 4r squared. So that implies that if we subtract c squared from both sides, actually let's just keep that like that, that we get 2r all squared minus c squared is greater than or equal to 0, which is absolutely bloody fantastic. Because now this thing is indeed greater than or equal to 0, which is exactly what we want. Because now that the stuff inside the square root, is either 0 or greater than 0, it's never negative, that means that x is a real number. And is x positive? Well, we have 2a over theta here, and here we essentially have 2a over theta squared inside there, yeah? So we have 2a. Now, the only way that x could be negative is if we take this negative value. If x is negative, then we have 2a over theta minus, well, we have 2a over theta squared minus c squared, then square rooted. So we have the thing square rooted, but we're taking something from it before we're taking the square root. And since we know that c squared is positive, 2a over theta squared minus c squared is obviously less than 2a over theta squared. So when we take the square root, this thing will definitely be less than this thing. So, therefore, you can say with confidence that x is greater than or equal to 0, and x will be a real number. So, that essentially completes our proof, essentially completes the problem, because what I've said is that if you solve this equation for theta, solutions will exist, and then you can shove your theta value into here along with your values of a and c, and regardless of what those values are, in this problem, x will always come out to be a real number. That's positive, which is exactly what you want, because this x physically will be a positive real number, which is great. Now, finally, I feel like we haven't had anything sort of solid at the end to finish with. So, I have one more thing which I want to write down, which will essentially be the final solution to this problem, where we can basically forget about theta now, because we've proved the solutions exist. So the final expression we can get is, if we go from our equation 3 again with r equal to a over theta, we have c squared equals 2a squared over theta squared. Now, I'm just going to write this quickly. Bring the theta squared up and the 2a squared down, we get c squared theta squared over 2a squared is equal to 1 minus cos of theta. And then we can substitute our value of theta now in for x, and we get the c squared over 2a squared multiplied by 2ax over x squared plus c squared over 4 is equal to 1 minus cosine of that thing, which is 2ax, sorry, that's a squared, over x squared plus c squared over 4. So if you simplify this, then we get 4a squared on the top, and we get an a squared on the bottom, so actually this a cancels with that a squared, and this 2 will cancel with the 2 squared to give it just 2 on the top. So we end up with 2 times c squared times x squared divided by x squared plus c squared over 4 squared is equal to 1 minus cos 2ax over x squared plus c squared over 4. And this is an expression only involving x, c, and a, as originally requested. And we can say with confidence that no matter what values of a, and c you put in here, you will be able to numerically solve this for your value of x. So, Ewan, I hope that's helpful, and thank you very much for watching.